Welcome back. So I come to you today, voice only, because I just want to give you some quick advice about how we're going to figure out what to do with the Hamiltonian in the position space representation. And what this means is that we're going to see if we can find certain wave functions that give us discrete energy levels. That is, can we solve the eigenvalue equation for the Hamiltonian in position basis? So when I look at this, I say, okay, well, the Hamiltonian, which is the kinetic energy plus the potential energy, if I choose to write this in the position basis, which we often do, especially because the thing that looks like it's unknown here is the potential, right? And the potential is the thing that exists in the position basis. I can write it as the second derivative with respect to x times some constants plus the potential energy. Okay. Now, if I look at this for a minute and I say, well, I'm gonna see if this operator has eigenvalues and eigenstates, I know that in the position basis, I'm really talking about solving a second order differential equation, right? Because when I act h on psi, right, the wave function, I'm going to get a constant times psi. That in and of itself is just a second order differential equation, an ordinary second order differential equation even, that I hope I'm going to be able to solve in the position basis. Okay. Now that the language there sounds awfully foreboding, but really you're ready for this, right? For the last 3 years, or maybe even 4 years, you've been spending a lot of your time getting ready to solve second order differential equations. And we're going to use many of the same solutions and many of the same techniques that you've been using over that entire time. So I'm going to give you some general steps now on how to approach these problems. The first thing that I always do is I plot the potential, right? I want to know, what am I getting into? Like, what is the potential going to look like, or what is the potential going to do, so that I can start to understand or start to conceive of what the eigenstates of that potential might look like, or what they might mean, or what those wave functions might look like when I look at them in space. And so on the left, I have the infinite square well. This is something that you saw in modern physics, where there's only a certain region of space where the wave function is allowed to be, right? And I can look at that and I can say, it's going to give me some idea of like what the boundaries are going to, right? I can start to think about what it means to be restricted to that piece of space. On the right-hand side, I have the finite square well, which is something that we'll do later in this week. Here, I obviously see that there's a region of space that has a lower potential energy than other regions of space, and that's going to give me an opportunity to have a wave function that perhaps is sort of mostly somewhere, but it's not necessarily forbidden to be anywhere. So once I have the potential, I go ahead and I actually plug it into the eigenvalue equation, right? And this is the equation that we've been waiting for, where I have h acting on psi is equal to e psi. And this is a second order differential equation, and so the step here, or the math, or the whatever that we have to do, is to try to find the two independent solutions to this problem. Now, don't let this get to you, right? Because at the heart of every problem where I'm doing this where I'm doing this Hamiltonian acting on the wave function, is a second derivative with respect to x and a constant, right? And that should remind us of one of our favorite differential equations to solve ever. Right. So from time to time, that's complicated by the presence of a potential, and that might affect how we visualize or how we think about our solutions. But deep in the heart of this second order differential equation is just the shoe. So once you've found those two independent solutions, if I'm going to be able to actually do something with them, or say that there are only certain allowed wave functions, I'm going to have to impose some rules. Remember, boundaries give us rules. No boundaries, no rules, right? So So you have to ask yourself, are there algebraic constraints on the system, such as boundary conditions or continuity of the wave function? Are there equations that I can write down that help to tell me that not all functions are a solution to that second order differential equation? Right? Now you as I said, you've been doing this, right? You've taken second order differential equations and shown that there are only certain solutions allowed. The interpretation here is just that those solutions now represent specific solutions to the energy eigenvalue equation, which means that our system only has certain allowed energies. And so if you have these two algebraic constraints, then you can quantize the system, right? You can say that the Hamiltonian only has certain allowed energies, and those certain allowed energies correspond to eigenstates of that Hamiltonian. And you've created the whole idea behind quantum mechanics, right? That only certain solutions are allowed. And the interpretation here is cool, but it really is something that you've been doing all along when you said, are there solutions to the second order differential equation? So I want to give you two more quick pieces of advice. One is that oftentimes, especially when we're starting out looking at different potentials, we will find that the potential is just a constant, and oftentimes that constant is actually zero. And if that constant is zero, I'll call that constant V naught. I can pull it to the other side, and I end up with exactly the shoe, right? I mean, this is nothing more beautiful than seeing the shoe appear naturally in yet another context, right? And therefore, if this is the shoe, you can say to yourself, well, then I know that the solutions, the two independent solutions here, are probably going to go like e to the I something, right? Plus or minus I something times x. And I'm going to leave that something up to us to figure out. But I'm choosing to use the complex parameterization here because, well, wave functions are complex, right? And so it seems to not be a bad choice for us to start with when we're thinking about what are the two possible, what's a good way to parameterize the two independent solutions of the case where the potential is a constant or zero, okay? See, all that time spent doing the shoe, totally worthwhile. Anyway, my second piece of advice is if the potential is defined piecewise, that is, if one region is this and one region is that and one region is that, it's best to actually solve the differential equation in each of these regions independently. And then I can get algebraic constraints from matching the fact that the wave function has to be continuous across the boundaries. And that's going to give us then the ability to write down the quantization condition from thinking about it as a boundary problem, right? But the boundary problem is one that the wave function has to be continuous across the boundary, and that's going to be really useful for us. Okay, so visualize the potential, write down the independent solutions, search for algebraic conditions that'll provide the quantization, and that's all there is.